In my second tutorial, I want to go over an example problem and introduce you to the input file. But before I start, I want to preface with the fact that I'm still learning Vulkan, and the information I'm presenting here is what I know, or what I think I know. It is mostly correct, but there will be mistakes and there will be omissions. Also, while you're learning Vulkan, I recommend that you go through the sample cases folder inside of Vulkan. Has a lot of good examples, and you will learn a lot of the Vulkan nuances by reading through these. And in today's problem, I'm going to pull the shock tube problem from this folder. What you're seeing here is the domain for the shock tube. You'll see that it extends 1 unit in the x direction and 0.3 units in the y direction. And the domain is split up into 2 regions, one on the left, one on the right. Also, I'm going to turn on here the grid meshing, and you can see that the grid here is pretty loosely defined, particularly in the y direction, but we don't really need a lot of detail in the y direction. And the way this problem is going to be set up is that there's going to be a large pressure difference set up initially between the left and right regions. And when this pressure region is released, it'll create a shock wave that'll propagate down the length of the tube and reflect off the end. The first thing we want to do when studying this problem is to take a good look at the input file. Now, Chapter 2 on NASA's Vulcan-CFD website, shown here, has a lot of detail on creating and modifying an input file. It is unfortunately written to an audience who's very familiar with CFD, and they skip a lot of the low-level details. There are some good resources online like cfd-online.com, and there are plenty of books published on the subject. I've created a folder here with the 2 files associated with the shock tube problem, the grid file, the GRD file, and the shocktube_rk.dat, which is the input file. Let's open up the .dat file, and you will see that it's pretty extensive. In this first line, we're specifying that we can assign up to 2 processors to solve this problem. Only 2 because there are only 2 blocks in the domain. This second line is less important. It deals with how the MPI package communicates with itself. Because we're primarily interested in the flow in the x direction, we're going to assign this to be a 1D flow problem. Here we're specifying the name of the grid file, shocktube.grd, and that it is a plot2D file. Here we're specifying that the grid is a multi-block grid, in this case it's 2 blocks or zones, and that it is a formatted structure. This unit here converts the arbitrary grid domain to meters. In this case, 1 grid unit, which is the entire length of the shock tube, is 0.3048 meters. The next 4 lines here govern the restart files. This is a neat feature in Vulkan that is pretty analogous to saving your progress in a video game. The 0.0 number after the restart n can be changed to any positive integer value, let's say 100. And Vulkan will create a saved file every 100 iterations where you can restart your code in case it crashes. Let's say your code crashes during a particularly unstable patch of your computation. With this feature, you can change your CFL number in your input file to something more stable and restart the code from your last restart file instead of from the beginning. The 0.0 here means that no restart file will be written. And also make sure that you use the same file name, in this case the .restart file, for both the in and output segments. This next segment controls how Vulkan saves your data. The plot on 4.0 specifies that it is a multi-block unformatted structure. I'm going to change this to 3 here later on. The 32-bit binary file specifies that it's a 32-bit binary output file instead of a plain text file. I'm going to delete this here in a little bit. Here I'm specifying that I want to save the next 4 variables, density, velocity, Mach number, and pressure. to the data output. In the output time history line here, I'm specifying that I want a snapshot of the data every one iteration. For most problems, this is going to put out a lot of data that you're not going to want to have to process. I would recommend larger values than one, typically. Here I'm specifying that I want to solve the simplified Euler equations instead of the full Navier-Stokes equations. Here I'm using a calorically perfect assumption instead of a thermally perfect assumption. In the next 6 lines here, I'm specifying that I want each block to be initialized with these total conditions. I'm using a Runge-Kutta solver specified below, and here are the input parameters for the Runge-Kutta. This next block of code deals with telling Vulcan some details about the different blocks or different zones that we're using. Here we're specifying that there are in fact 2 blocks, as shown here, and that there are a total of 8 boundary conditions, 4 for each block. 1, 2, 3, 4, 5, 6, 7, and 8. There are 2 there at the interface. We're also telling Vulcan that we're going to classify 4 different types of boundary conditions. 1 for the walls, 1 for the end caps, and 1 to initialize each block. We don't have any boundary condition objects, so 0, and there is 1 cut boundary condition. And the cut boundary condition is the boundary between the blocks that allows flow between them. We don't have any patch boundary conditions, and we want to save the time history for both blocks. Next, we want to initialize the blocks, and we're specifying 1 block because we're initializing both with the same line. The 0 under the block number specifies that this line will initialize every block in the domain. Because we're solving the Euler equations, there's no viscosity, so we put no under the ij and k viscosity parameters. We also specify that we want to save the data for this block, so yes. And we assign this block to region number 1. If we did want to initialize each block independently, we would have a line for each block like this. So block 1 and 2, and you type in whatever parameters and assign them to whatever regions. In addition, I would need to update the block config input above, which is presently 1 to 2, to tell Vulcan that there are in fact 2 blocks, or 2 lines of code to read in for the block initialization. The next 10 or so lines of code initializes the solver for the first region. And the previous line, we specified that blocks 1 and 2 belong to this first region. There may be situations where you want multiple regions in your code. You may have hypersonic and subsonic regimes, and you want a different algorithm or different scheme to solve each of these regions. With this region tool, you can create multiple regions and solve them with different schemes. Depending on how you set up your problem, there could be a lot or very few lines of code in this section. For this particular problem, there are only 1, 2, 3, 4, 5 sections of code. This first section, shown highlighted here, sets up an elliptic and active solver and gives it a number of other parameters. This second segment of code instructs Vulcan when to stop the computation, and in fact, it gives 2 conditions for stopping. The first, Vulcan is instructed to solve the first and only multigrid level. This is the one, for 50 iterations. Second, Vulcan will stop if the residual error, both relative and absolute, reaches 10 to the negative 99. Obviously, this is incredibly small, and the input file was expected to hit 50 iterations long before the residual cutoff was achieved. For computations where you want the problem to stop when it hits steady state, use values like 10 to the negative 6 or 10 to the negative 10 instead. The third segment here provides some instructions for the multi-gridding and some other damping terms. This fourth section has to do with some of the turbulence model control data. And the last section here specifies the computational scheme and the time-stepping method. Here we're using a Runge-Kutta scheme and a delta t time-stepping method, and there are alternatives for both of these in Vulkan. The delta t time-stepping scheme is a fixed time-stepping method that can be used to output the solution. We've been referring to this as the time history throughout the input file as it's evolving. Alternatively, you can use a CFL number-based method such as local, which it generally achieves a faster steady-state solution but cannot output time history. The VAR-CFL option here can allow for a auto-compensating CFL time-stepping scheme. The CFL values input, shown here with a value of 2, allows for a CFL and time-stepping profile instead of a single value. Below you can see 2 values. Because we're using a fixed time-stepping scheme, the values are time steps instead of CFL numbers. At iteration 1, the time step is set to 3.7 microseconds, and at iteration 10, it is also set to 3.7 microseconds. If different values were chosen, Vulkan would ramp up or ramp down the time steps between these iterations to provide a time-stepping profile. This could be advantageous if the program is very sensitive to instabilities when it first starts up. You could start with a slower time step and ramp up to something quicker. And finally, at the end of the input file, we specify the boundary conditions. As we previously mentioned, we're collecting the boundary conditions into 4 groups: tube, cap, driver, and driven. Tube is a slip wall condition along the sides, cap is a slip wall condition at the ends, driver initializes the high pressure region, and driven initializes the low pressure region. Next, we specify which wall belongs to what boundary condition group. Here we're specifying that the leftmost boundary on block 1 is a cap, and that the rightmost boundary is a driver, that the bottommost is a tube, and the topmost is a tube. For the second block, the leftmost is a driven, rightmost is cap, bottommost is a tube, and topmost is a tube. The rightmost column here specifies the order in which to initialize your boundary conditions. Since most of these boundary conditions are slip conditions, they don't need to be initialized and are set to 0. Since driver is set to 1, it will initialize block 1 first, and driven, which is set to 2, will initialize block 2 second. This next section specifies a single cut condition, and this cut condition allows flow between the 2 blocks. Finally, we specified that both block 1 and 2 should be recording its time history. And that's it. But before we start, I want to change a few values. First, I want to change the output files to a plain text format that I can easily edit. The time history blocks weren't quite set up right, so I'm going to change that real quick. To make the solution more interesting, I'm going to have it solve 500 steps instead of 50 steps. I am also going to turn on the restart files just to show it off. And save. So right now I only have the grid file and the input file in this directory. So I need to make the hostnames file. And as I discussed in the first tutorial, we will write the Vulcan execution command. I want to show that there was a blip there that were both processors turned on, just very briefly while it solved it. Now that it's done, you'll notice that Vulkan produced a lot of files, and we're going to go through those real quick. The output file here, it logs the progress of the solver as it works through the problem, and it will also explain any errors if they are encountered. These next files are the restart files. Vulcan will only ever keep one set of restart files at any given time. And finally, these TEC files will keep track of various numbers, such as the errors. This file here, for example, shows a column of the iteration number, or the cycle number, and a column of the L2 residual and the log of the L2 residual. I've written a MATLAB script that will plot this file with time as the solver is ongoing, so I can keep track of the error. The final solution files are placed into the plot3d file folder. The first file here, the .f file, contains the final solution to the problem. The second file, the .g file, is the grid file generated in conjunction with the .f file. I have found it to be buggy and I do not use it. This third file, I believe, is a field view file, and since I use TechPlot as my post-processing program, I can't use this file. And the final file, the .name file, contains a list of all the variables that were saved. I'm going to create a new name file because when you load the time history data, which we're going to do here in a minute, into TechPlot, it makes time an additional variable, and it'll mess up the naming when you load this name file. So I am going to open it up and add time in as the first variable and save. And finally, let's look at the time history files. Vulcan produces 1,000 of them. This equates to one file per each zone, per each time step. To merge these files into something that TechPlot can read, we're going to navigate to the folder and run a script called time merge. The first input for time merge is to type in the root name, which in this case is shocktube time, shown here. Then we type in the total number of blocks, which is 2, and we say to process all of them. I prefer formatted plot3d files, and I tend to delete the old ones. And this results in 500 files, one per each time step instead of 1,000 files. I have already loaded these files into TechPlot, and I'm going to show you what the result looks like. Here you see pressure plotted, and the left region is the high pressure region, and the right region is the low pressure region. And as the solution evolves, you can see the shock wave propagate to the right and reflect off the wall. And that is it for our first example. There was a whole lot I did not cover and even more that I do not know. And hopefully you now know enough to get started with Vulcan and be a little dangerous. Good luck.